All right, just all right. Recording has started. This is day one of 5.11. So we have 3 days left of lessons. Then we have the review on Friday, and then your test is next week on Monday. NWEA is on Tuesday next week. And don't forget, if you show improvement on that test, if you want to be, you are exempted from taking the math final, which is worth, I think, 125 points. But if you still want to take the math final, you can, even if you're exempted. And I think I said in the email that if you if you're exempted from the final, but you still want to take it, and you take it, and it lowers your grade, I will then go in there and I will remove that grade. But anywho, so we only have 3 lessons left in this course. Then after that, it's reviews and testing. Review for the Unit 5 test, and then review for the final. And then we're done. Three new lessons. Learning new things in this class is almost to an end. It's sad. Okay, so this, I have the Mario star here. This shows that this is a TGA problem. So you have 3 TGA problems. This is one of them. This is actually last year's TGA problem, exactly. You need to consider the polar equation, r equals 3 sine of 2 theta. You need to complete this table by just plugging in these values into theta, hitting enter, and then, well, you want to round your answers to the nearest tenth. So 1 decimal place is fine when you put these in. And then after you do that, you want to graph them. So you want to use the polar graph, and then you want to plot, well, the angle and then the radius, angle, radius, angle, radius. So yeah, so let's kind of just quickly go through it. Remember your thetas, these are in radians, so make sure your calculator is also in radians. If it is not, well, your numbers are going to be very, very wrong. And that's bad. All right, so just quickly going through it, if you were to enter all these, you should have gotten all those points. Everyone agree? It's remember I typed these by hand, so it's possible I maybe made a typo somewhere. It is. So this problem, it's not difficult. It's just time consuming because you have to like go through and enter all of the values, and that's kind of a pain. There is a way to do it in Desmos, and I'm pretty sure I showed it when we did this lesson, but I don't have it in front of me. But I'm pretty sure we did. But if not, doing it by hand is just as easy. Just takes longer. All right. Something to remember. So you have the angle. These aren't negative, so you're just kind of going around the circle, right? But remember, this is radius. So if we rotate to 2 pi over 3 and the radius is negative 2.6, what do you have to do? Rotate 180 degrees. Yeah. Yeah, it's just the diagonal, right? So remember, you need to review that lesson that we did this in. You go to the angle. If the radius is negative, that means we're going to have to rotate 180 degrees to the opposite quadrant.
To clarify, you can't just follow the line down or up, right?
You can. Yep. And I'm going to kind of show that. So on this next page, this is what your graph should have looked like. So like your first, I'm gonna keep going back and forth. 0, 0 is here, and then pi over 6, comma 2.6. So here's pi over 6, and then 2.6 is roughly right here. So this is where your other point should be. Antonio, would you do me a favor and use blue? And where I point, will you put a dot for me?
I'll attempt to, yes.
Nope, that works. Nope, that works. I like that. All right. Put one right here, too, at the origin. All right, let's go back to the previous page. And then we are at pi over 4, comma, radius 3. So pi over 4 is here, radius of 3. So right here, if you could. And then the next point is pi over 3, comma, 2.6. So here's pi over 3, and then 2 points. Hang on a second. Pi over 3, radius 2.6. I feel like...
Sir, I think it'd be right here. That's pi over 3.
Oh,
right there.
Oh, this is polar, not Cartesian. I'm so silly sometimes. Yeah, I see it curves. I was looking straight up like it was Cartesian. Thank you, Antonio. Yes, 2.6. Thank you. Thank you. It's right in front of me, and I don't know what I'm doing. All right, then we got pi over 2, comma, radius of 0. So again, that's just at the origin. Don't do anything. It's already there. Okay, so here's another one. 2 pi over 3 is the angle, and then negative 2.6 is the radius. This is what I was talking about. So 2 pi over 3 is here. Now 2.6 would be here. However, because it is negative, you have to rotate 180 degrees, or just basically follow this diagonal down to this one. So that would be the coordinate for 2 pi over 3, comma, negative 2.6. So make sure you review that lesson from a couple weeks ago. All right, we'll do one more point. 3 pi over 4, comma, negative 3. So same thing. We have 3 pi over 4. Radius is negative 3, so you just have to rotate 180 degrees to this point here. So, and that's what you do. You go through your entire table, you plot your points, and then as you go through, you need to connect the points. So that's why from here, we would follow this path through these 3 points, back around, and you can kind of guess it probably continues to follow this path here once you finish all your points. So on your TGA, you're going to have to do that. I do want to see your points. Like we did a few of them here. 3, 4, 5, like 6 points here. And then obviously the points connected. So that is one of your TGA problems. Pretty straightforward. It just takes time. And the good thing is if your table's messed up and you plot your points and your graph doesn't look good, like it should be symmetric, right? If your graph isn't symmetric looking and like, I guess, pretty looking, you probably messed up somewhere. So this one's pretty straightforward. You can pretty much self-check it just by looking how you graph it. And, that's one of the problems. Any questions? And yes, we are in radian mode because your theta, your table is giving the angle in radians. So because I give you the angle in radians, we must be in radian mode. All right, let's go on today's lesson. 5.11, day 1 of 3, we're going to graph parametric equations.
We have a question in chat.
I have a question quick for the TGA problem. It's okay if we just draw the graph onto the picture in like GIMP or something, right? Because that's how I do all my work and stuff, so I don't have to mess with printing stuff out.
Yeah, that's fine. If you can, when you use GIMP, make sure you use like blue points. Don't use black on a black line. And if you want to like overemphasize the radius of those points, just so I can see them, kind of like Antonio did, I think this is totally fine what he did. But yeah, I like GIMP.
Okay.
By the
Cool.
way,
Thank
GIMP,
you.
people who don't know what GIMP is an open source Photoshop-like application. So
Dr.
it's free. Really nice. Mhm.
So for on the other side before this one, so for 3 sine 2 pi over 6, so you got 2.6 from my calculator. I got 1.4 for the first one. Yeah.
Which one? Pi over
For
6. Okay, it's right here.
yes.
Did you put this in parentheses?
If I put the 2 with the pi 6 in the same parentheses, it gives me an error. I have to.
So type in 3 sine parentheses 2 times pi over 6 in parentheses.
Okay. 1 second.
See if that gives you 2.6.
Okay, so it gave me 3 radical 3 over 2. So then, okay, yeah.
All right, hit the
2.6.
hit the SD button. Yep.
Okay,
You got it.
thank you.
You are welcome. All right, we good to go on, everyone? Okay. All right, being recorded. All right, functions written in parametric form. So functions, as you have found in your high school career, consists of 2 variables. The input, which is the independent variable. You learned that probably back in, I'm going to say grade school, maybe like 5th, 6th grade, maybe. And your output, which is your dependent, which is usually your y variable. So your input is your x, which is independent. Your output is your y variable, which is your dependent. All right, so with parametric equations, both not exclamation, but yelling, both of the variables x and y are dependent variables, and there is a third variable, usually t. So what we're used to, at least for a Cartesian y equals mx plus b, for example, your x was your input, your y was your output. Input is your independent, output is your dependent. But for parametric, both x and y depend on what t is. So x and y are both dependent. Your input t is your independent. Hopefully that makes sense. And t is known as the parameter, hence the name parametric. So for example, we have the function, this f of x equals x squared. You will see 2 functions. So we can convert this from the standard rectangular form to parametric. And when you convert this single equation, you create 2 equations and you get a third variable out of it. Pretty amazing. Okay, the purpose. All right, so unlike typical algebraic functions that have a fixed domain, parametric equations can essentially have any domain you want. And like it says, while avoiding undefined parameters, of course. So like dividing by 0 is not good. For example, the function f of x equals x squared has a domain of all real numbers. So that means that we can input anything in for x and we'll get an output. So what does this graph look like? So in chat, go ahead and tell me what this graph looks like. What's the shape? It's a parabola. Yep. And what does it look like? I know. Actually, you can say, "Oh, parabola. It's a parabola. It looks like a parabola." Yeah. In other words, a parabola looks like a U, right? A U opening up or down. That's a parabola. So, but yeah. And this is actually also called a quadratic. So you can input anything. It creates a U, opening up or down. In this case, this one opens up. We learned about that last semester. All right. So, but the parametric equations, x of t equals t and y of t equals t squared, can be set for t along the intervals 0 to 1, -2 to 5, or 8 to 10. I just chose random numbers. There's no rhyme or reason of why I chose these three. Basically, you can choose anything for your interval of t. Doesn't matter. Well, it sort of matters, and we'll get to that a little bit. All right, furthermore, parametric equations can help graph equations that do not result in functions. So if you were to type this in like Desmos, it creates a U, but in certain cases, like if you wanted to graph like an ellipse or a circle, like I have here, you couldn't just have a single function to do that. Well, with parametric equations, you can. It's pretty neat. Well, this is a very wordy presentation. Where's the fun? It's going to start soon, I promise. All right, so how to graph parametric equations. So just like with traditional functions, we created a t-chart, and parametric equations are the exact same, only with a third column for t. So but when you create your t-chart, you are only going to plot the x and y coordinates. So that t value is only used to find out your x and y values. So you are not graphing t. We're not creating a three-dimensional graph. Hopefully that's clear. So even though we have a third variable, you're only going to graph or plot the x and y values we find. All right, lastly, all right, you put an arrow in the direction of the increasing t value to indicate how the graphs started and where it would end. You know what? I wrote this, but in my examples, I'm pretty sure I forgot to do this step. So I'm going to have to write this in on the next few pages. All right. All right, for example, we want to fill in this table and we want to plot the points. Then we want to sketch the parametric equations for t, and t's on the interval of -2 to 6. Okay. So I already created the table with our three variables. We already know the two functions. X of t is this, and then y of t is this. And then because the interval is from -2 to 6, well, in the table, we start at -2 and we go all the way up to 6. So this, again, just like bell work, this is time consuming. You're going to have to plug in -2 into this, hit enter, write it down. I would probably recommend doing your X column first, because then you can just kind of hit the up arrow, the back arrow on your calculator and just change your input from -2 to -1 to 0 and so forth. Don't forget to put it in parentheses. So everyone quickly do the X column. I'm going to give you, I'll say 1 minute to do as many as you can in this table. So if you finish your X column, go on to the Y column.
What do we round to, if anything?
Oh, round to 1 decimal place is fine.
Okay, thank you.
Yep, 1 decimal place, please. Sorry, I forgot to put that. 1 decimal. I wish Neuro allowed me to go on to the next slide and do stuff to that slide, but it doesn't. Because I forgot to cover something on the next slide, but it's okay. All right. In chat, list the first 3 or 4 values of X that you got. As many as you found. Yeah, it's not an order triplet. So it's not X, Y, T. Decimals, please. Decimals, please. So we got 2, 2, 1.4, 1, 1.4, 2, 2, 3.2. I would agree with Antonio. Yep. Yep, those look good. So, this is very the process is very, I think, straightforward. It's just plug and chug. You just plug it in, hit enter, write down the decimal, go to the next one, plug it in, hit enter, write the decimal. And then once you do your X column, you go to your Y column, do the same thing. And that one's pretty easy. You can probably do that in your head, right? -2 minus -2. Well, that's 2 plus 2, so that should be 4 here. And then you're going to have 2 minus -1, so 2 plus 1 is 3. It looks like it just goes 4, 3, 2, 1, 0, -1, -2, and so forth. To me, that's what the pattern looks like. Would you all agree? Yeah, so that one you probably do in your head, but for some reason, I personally have trouble with negative numbers. And I don't know, whatever reason, me subtracting numbers, I don't like it. Nightmares. But anyway, so you should get this. And pretend that wasn't there. Okay. Next, what you're going to do, Antonio, do me a favor. Hold on, let me see if it fixes it. Oh, they fixed it. Okay. Next, we are going to plot these points. So remember that the t value is only used for deriving the table. Once you derive your table, you have your x and y, though that's your ordered pair. 2.2, 4, 1.4, 3, 1, 2, 1.4, 1, and so forth. So you're going to plot those on your graph just normally. And I already did it, but I didn't do the points. So let me go and do a few. So the first one is 2.2, 4. 2.2, 4. So that would be this point here. And then we're going to have we have 1.4, 3. So that's this point here. And then you're going to have your 1, 2. So do you see how I boxed my x and y values? I did that so I wouldn't make the mistake of using my t value as my x value, because that is a common mistake. After creating your table, you accidentally use those t values, and you can even like lightly maybe draw a line through it so you know not to use it, because that would be a big mistake. All right, then we keep going. We're going to have 1.4, 1. So that's this point here, and so forth. So I'm just going to quickly.
Sir, this line is way off. There's no way that's 3.1.
This definitely is, because I did it in Desmos. It has to be. All right. Now the part that the part that I didn't do is this line right here. So you have to create these arrows. Now in your modules, they're going to show that. Let me show what that looks like. Because I believe on your test, you have one of these types of problems, and you have to know what those arrows mean. So you want to put the arrows in the direction of the increasing t value. So that all that's going to look like is this. See how my t value is increasing? All right. And this really just shows where we started. So if I didn't have these arrows showing you this is the path, we really couldn't, I guess we could guess, but we might probably be wrong most of the time. We wouldn't know where the starting coordinate was. And because t value we increase, remember smallest to biggest, this is the coordinate, so that was the first point. So we have an arrow going to, well, increasing t value. So this is at t equals -2. This is at t equals -1. This is at t equals 0. T is 1. T is 2, and so forth, right? So when you see this on your quiz, on your test, and those modules, that's what this is showing you, is your increasing t value. Is that clear? All right. Now let me show you something really cool. Sharing your screen is so many clicks. I don't like it. All right. All right. Everyone see my screen?
Yes.
All right. So I graphed this in Desmos. So I know some of you are wondering, how do you do this in Desmos? Well, this is how, and I'll share this link with you in chat, people that are here. I'm guessing this is red. My red line is the actual graph. And because it's parametric, even though you create a third variable t, you're only going to plot x and y. So that's why I have this as an ordered pair. This would be the x value. This is the y value. So x of t is the radical t squared plus 1. Y of t is 2 minus t. So in order to graph it in Desmos, you have to write it in this format. And then it creates this interval line. And the interval of t is from -2 to 6. So let me turn off my blue. So that's that. Now, if I changed like this 6 to 5, see how my graph is smaller? Or I change it from -2 to 2? Well, it just makes the table smaller. The interval for this problem is -2 to 6. What we have. Now, this next line of the code or the equation that I created, it's the exact same thing, but with, instead of t, I put a here, and I don't have an interval. And what this does, and this is, I wouldn't call this advanced Desmos coding, but it kind of is. I don't know. This creates a coordinate, whereas this is an interval, so it's graphing every point from -2 to 6. So if you think about it, every point, I'm basically graphing an infinite number of points, creating a line. Here, I'm graphing a point, and then on this next line, I am defining what that point is. So I can make this at -2, and that's where it's showing my first point. So if I click that, hey, look, there's the table values that we found by hand, right? 2 points, 2 comma 4. I can change this to t equals -1, and then we get that point. And I can write that down in the table, and then go to the next one, and next one, and next one, and next one. And something cool about Desmos is I created a loop, so when I hit play, it shows the path. So we can now see the path of as t increases. How cool is that? I think it's pretty cool. I was super amused by this. I was super amused. Yeah, when things move, I think it's wow, it's moving. Anyway, so that's this graph graphed in Desmos. So I will let me share this link for all of you. And I would so this link that I'm going to share in chat, you might want to save it like in a Word document so you have it.
Do we need to use this, or can we just do it by hand?
Oh, you do it by hand, but some of you like to I guess reference back to what I did to maybe create your own or something. I don't know. It's there
I
if
like
you want to
software
use
that's
it.
taking a long time.
There if you want to use it. Well, there's a link in chat. Let me stop sharing. Okay. All right. So here is another one. Let's do. I'll give you all. Let's say 2 minutes to fill in these values and graph it. Oops. 2 minutes. And again, just round to 1 decimal place. Uh-oh. I'm looking at my answer for this problem, and I didn't type it right, so that's cool. Oops. Well. How did I mess that up? Oh, boy. All right. What did everyone get for your X column? What are those values? I think you are all right. And write those in. I'm not even gonna. I'm gonna quickly blast by the next page so none of you see the tragedy that I created. All right. And then what are your Y values? Negative 4.5, negative 2. You said negative 0.5. Okay. I would agree with those. Yes. Volunteer one to try to graph this for us. All right, Julia, go for it. On the board, yep. Julia, don't forget these values go negative again. So once you hit 0, you go back down. There you go. Points look pretty good. And then, with the best of your ability, you are going to connect your points. All right, and then what's our last step? Everyone in chat, what's the last step that we need to do? The arrows. The arrows. Yeah, this shows the direction of the T. So you would have like this, this, arrow, arrow, so many arrows. Yep. And then we're done. Pretty simple. And then here's my graph. It's pretty funny. I did this in Desmos ahead of time, but for whatever reason, my table of values and the actual graph is wrong on the next page. I'm just really good like that. But here, just like the first example, you can see the direction of T by that moving point. Pretty neat. Pretty neat. Let me share this one with you too, if you care to have it. Nothing to see there. Nothing to see. All right, this other example. So those first two examples we had restrictions, but you can have parametric equations that don't have a restriction. For example, we have these two. X of t is 4 sine t, and then y of t equals 4 cosine t. Why do you think we don't necessarily need a restriction here? Well, yeah, but going on forever could be, that could go for true for anything, right? It can go like for the previous example, we could have gone on forever too. Sine function. So yeah, this is a trig function. This is just like the bell work. It's very cyclical. At some point it's going to repeat, right? All right, so let's quickly go through this one. Looks like we're running out of time. We got 12 minutes left. So we just like before, we create our table. Now for this one, make sure you are in radian mode. And just like before, we're just going to plug these values in from -4. Now I chose, if you're wondering, why did I choose these values? Well, I just chose them just because. I could have started at like -5 and gone from -5 up to +5. I could have started at -2 and went to like, I don't know, 10 or something. I chose this just to give like a range of some negative and some positive values. It doesn't matter. It doesn't matter. But that's what I chose for my table. And on your modules, your quiz, on your test, you may have a choice also. But on your TGA, I tell you which values to use on your table. So the values that I chose, I got these, and then I plotted the points. And it creates a circle. And I actually have a link for this one too. Sharing is so difficult.
Oh, okay. Well, I was about to help explain.
Okay. Does everyone see this?
See it.
All right. All right. So just like the previous examples, I have this one actually creates the graph. This one creates the point that we can kind of watch and follow to see the direction of t, which I still have to put my arrows in. But and for this, like I went from -10 to 10. I could have made this from like -5 to 5. At some point, like if I make this, yeah, if I make it from -5 to 5, it still draws it. If I go from, if I did from like 0, yeah. So at some point, if I don't have enough values, I don't create my full rotation. Now, it should go. It's from 0 to 2 pi, right? One full rotation on a circle is 2 pi. So if I do 2 pi here, yep. See how it creates the full circle? So my table could have been from 0 to 2 pi. But remember, if your period is different, like if your period isn't the standard for sine or cosine, like we're doing here, and you choose 0 to 2 pi for your table, you actually may not get the full period of values. That makes sense. So really, just choose a big enough range that you can probably hit all the values and more without thinking too hard about it. All right, so then for my point, I went ahead and I made this from -20 to +20, and I didn't include a step, which we can step. If I click this, I can make a step of like 1, but then you see the circle kind of jump around, and I wanted to show this as a smooth rotation. So as your a value increases, the orbiting of your point of the location orbits too. So by going from -20 to 20, I'm doing, I don't know, I forgot what it is, maybe like 6, 12, 18, maybe like 7, almost 7 rotations, maybe 8 rotations. I don't know. Math is hard sometimes. So yeah, so by knowing the rotation of this point increasing your t values, we can now draw the arrows in. So let's do that. And I will give all of you this one as well. So there's that link. And then I need to go through and put my arrows in.
Sir, quick question. Dr. J.
What's the question, sir?
How can you explain how you got negative 2.62?
Magic.
Okay.
Let me see. The first one here?
Yes, this one right here.
I plugged in -4 into t. So 4 sine of -4 hitting enter will give me -2.62.
He said sir, guys.
At least I hope it
Sarah.
does.
Did you do it in rad mode or?
Are you telling me these aren't right?
Yeah. Yeah, because I tried it right now too, and it's not
Hold
working.
on, let me go back to my.
Also, Antonio, I hate to break it to you, but he said Sarah. Shade.
It's fine. He has a hearing problem.
So when I plug in -4, I know what I did wrong. Oh.
Did you flip the equations?
I did. So these values are wrong because when I typed it into Desmos, the x should be 4 sine t, and in my demonstration, I had it written as 4 cosine t. Let me go back and share that and see my mistake. Whoopsies. All right. So see how my x of t is 4 cosine? Well, it should be 4 sine. So I would just change that to sine. And then the y of t becomes 4 cosine t. Oops. And then I change this one too. So now, all of you should have got 3.027 for x of t when t is -4, and -2.6 for y of t when t is -4, right?
Yeah, it's just your values backwards.
And because they're backwards, the direction that's rotating is also the other direction. So let me fix everything. All right. You know what? It's just easier for me just to rewrite these equations the way that I originally graphed it. So I'm going to do that. So this first one should be 4 cosine t, and this one should be 4 sine t. Look, I fixed my mistake. And now the table of values is wrong. So all the work that all of you just did on your own paper is wrong. Sorry. So maybe this is, you know what? I may have done this on purpose to show that using Desmos, even though it's a shortcut, can cause other problems.
This is why app calculator is the best calculator of all time.
This is why doing it by hand is the best way. I was being lazy and trying to do it the fast way. So By having those equations swapped, it caused your t values to rotate the other direction. The graph you get is the same, and that's because if you understand trig functions and how they work, this has a amplitude of 4, and so does this. So in the x direction, the amplitude is the same as the amplitude for the y direction. If they were different, like I say that was a 4 and that was a 2, you would have an ellipse instead. Football. All right, let's one last slide here. And oh yeah, looking ahead. So, all right, so tomorrow and say Tuesday. Today's Tuesday. Yeah, so Tuesday and Wednesday. Or sorry, Wednesday and Thursday, or day 2 and day 3. We're going to look and how these connect. One with the standard Cartesian equations. We'll do that tomorrow, and then on Thursday, this is probably one of my favorite lessons of the term. I think it's so cool. This is using parametric equations in word problems, and to show the projectile motion using like gravity and velocity, like initial velocity. It's super cool to show the path of objects, like whether it be like a football, baseball, cannonball, basketball, whatever. It's neat. I think the lesson on Thursday, if you like physics, you're going to love the lesson that we're going to learn Thursday. So I thought it was super cool. Anyway, other than that, any questions before we stop the recording? All right, guys. Well, thanks for coming. And as always, I hope you learned something.